Chapter 6 of History of Chemistry, Volume 2 by Sir Edward Thorp. This LibriVox recording is in the public domain. The Periodic Law. In an anonymous essay on the relation between the specific gravities of bodies in their gaseous state and the weights of their atoms, published in Thomson's Annals of Philosophy in 1815, the attempt was made to indicate certain consequences which seemed to follow from Dalton's law of gaseous volumes as generalized by Gay-Lussac. The author of this essay was subsequently discovered to be a medical student named William Prout, noteworthy as having been one of the first to point out the suggestiveness of the numerical relationships which occur among the atomic weights of the elements. This paper is usually assumed to contain the statement that the atomic weights of the elements are multiples of that of hydrogen. As a fact, however, this hypothesis is nowhere explicitly stated in the paper. The inference was practically due to Thomson, who strove to support it by experimental proof of so weak a character as to draw forth the remark of Berzelius that much of it appeared to have been made at the writing desk. Nevertheless, the occurrence of such numerical relationships continued, as already stated, to excite speculation. Duberreiner, in 1829, pointed out that in certain groups of correlated elements, consisting each of 3 members, the middle member had an atomic weight practically identical with the arithmetic mean of the atomic weights of the others, and similar observations were made by Gmelin, Dumas, Gladstone, and Strecker. An approach to the recognition of the general law underlying these facts was made by Newlands in England, and independently by de Champ-Courtois in France, who were the first to indicate that the properties of the elements are related to their atomic weights. This conception was developed by the Russian chemist Mendeleev. In Mendeleev's arrangement, first published in 1869, the elements are so grouped that their properties are periodic functions of their atomic weights. The general statement of what is now known as the periodic law may be put in this form. If the elements are arranged in order of increasing atomic weight, the properties of these elements vary from member to member of the series, but return more or less nearly to the same value at certain fixed points in the series. This is observed to occur in the atomic value or valency of the several members, also in their specific volumes, melting points, ductility, hardness, volatility, crystalline form, thermal expansion, refraction equivalents, and conductivities for heat and electricity, in their magnetic properties and electrochemical behavior, and in their heats of chemical combination, etc. The first chemist of note to grasp the significance of Mendeleev's generalization was Lothar Meyer, who, dealing at the outset with one of the characteristic properties of the elements, namely their specific or atomic volumes, that is, the values obtained by dividing their specific gravities into their respective atomic weights, greatly developed the principle of periodicity, representing it graphically in a most striking and suggestive manner, leading up to a classification almost identical with that of Mendeleev. Since the date of its promulgation, the scheme of classification of the elements in accordance with the principle of periodicity has experienced certain minor modifications necessitated by fuller knowledge, but in its essential features it remains very much in the form devised by Mendeleev. The discovery of the so-called inert and radioactive elements required that their relations to the periodic law should be defined. Their inclusion raises no fundamental difficulty. Indeed, the generalization seems to adapt itself to the far-reaching considerations which spring from modern views of the nature of the atom, its electrochemical relationships, and the orderly arrangement of the corpuscles of which it may be composed. In the 1905 edition of the English translation of his famous Principles of Chemistry, Mendeleev has given a table which may be said to embody his final views concerning the systematic classification of the elements. This is reproduced on page 82. In this table he postulates the existence of 2 hypothetical elements, X and Y, the former of which he regards as identical with the physical ether, while the latter is an analogue of helium, possibly identical with the coronium of the solar coronal atmosphere, with a molecular weight of about 0.4. The striking feature of Mendeleev's generalization is its universality. In this respect it differs from all previous attempts at natural classifications of the elements. These were limited and partial, and therefore unsatisfactory. Nevertheless, it is easy to trace in them fundamental conceptions upon which Mendeleev built. Mendeleev, in fact, gave a great extension to ideas with which the chemical world of half a century ago was more or less familiar, and doubtless it was to this circumstance, combined with the remarkable boldness and comprehensiveness of this extension, followed almost immediately by a most striking series of confirmations of his own provisions, as logical consequences of his generalization, that secured for it attention and ultimately universal adoption. The periodic law, in the words of its author, is the direct outcome of the stock of generalizations of established facts which had been accumulated by the end of the decade 1860 to 1870. It is founded wholly on experiment, and is as much the embodiment of fact as are the laws of chemical combination. It was based upon the adoption of the definite numerical values of the atomic weights, as indicated by Cannizzaro, as a consequence of the hypothesis of Avogadro, and upon the assumption that the relations between the atomic weights of analogous elements must be governed by a general law. The application of the periodic law immediately led to the redetermination of certain atomic weights, and to the correction of their assumed atomic values. At the time of its enunciation, the determination of the valency of an element was purely empirical, with no apparent necessary relation to that of other elements. We find now that the valency is a matter of a priori knowledge, just as much as any other property of the element. The amended values for the atomic weight and valency of a number of elements thus demanded by the law have now been confirmed by all the experimental criteria employed by chemists. The generalization further indicated the existence of new elements. It pointed out their probable sources and foretold their properties. Instances of this power of divination in the law are to be seen, as already mentioned, in the discovery of gallium by Lecoq de Bois-Baudran, of scandium by Nielsen, and of germanium by Winkler, the existence and main properties of which were severally foretold by Mendeleev in 1871. The promulgation of the law was heralded as a proof of the validity of the conception of a primordial matter. It was held that it can find a rational explanation only in the idea of unity in the formative material. But its author would not admit that his generalization had any relation to the Pythagorean hypothesis. The periodic law, based as it is on the solid and wholesome ground of experimental research, has been evolved independently of any conception as to the nature of the elements. It does not in the least originate in the idea of an unique matter, and it has no historical connection with that relic of the torments of classical thought, and therefore it affords no more indication of the unity of matter or of the compound nature of the elements than do the laws of Avogadro and Gerhardt, or the law of specific heats, or even the conclusions of spectrum analysis. None of the advocates of an unique matter has ever tried to explain the law from the standpoint of ideas taken from a remote antiquity, when it was found convenient to admit the existence of many gods, and of a unique matter. The reader who desires a fuller exposition of the principles of the periodic law must be referred to special treatises on the subject, or to the larger manuals on general chemistry. It must, however, be stated that, while many facts discovered since the original promulgation of the principle, and since its development by Lothar Meyer, Carnley, Thomson, and others, are consistent with the law, other facts, some of which were known before 1870, are apparently out of harmony with it, or at all events await a fuller interpretation. For example, tellurium is not in its proper place in the scheme if its atomic weight, 127.5, has been correctly ascertained. Cobalt, 58.97, and nickel, 58.68, have atomic weights so closely accordant that their properties and those of their corresponding compounds should be very similar, and in fact almost identical, but such is not the case. Indeed, it has been said no provision of the periodic law would have led to the discovery of nickel. Similar considerations apply to manganese, chromium, and iron. The atomic weights of these elements are less widely different than the differences in their properties and the divergence in their chemical relationships would seem to require. The relative positions of argon and potassium are also not consistent with the law. There are difficulties, too, connected with what we know at present concerning the atomic weights of the so-called rare earth metals. In spite, however, of these seeming anomalies, it can hardly be doubted that the periodic law is as much the expression of a natural law as is the law of gravitation, although it is possible, and indeed probable that, as we now define it, it is only the first approximation to the truth, and that as our knowledge becomes more precise, Mendeleev's classification in its present form will require modification and extension, just as Mendeleev's own scheme may be said to be a modification and extension of the attempts at the rational classification of the chemical elements made by his predecessors. Dmitri Ivanovich Mendeleev, with whose name this fruitful generalization is indissolubly connected, was born February 7, 1834, N.S., at Tobolsk, in Siberia, and was the 14th and youngest child of Ivan Mendeleev, the director of the gymnasium at that place. Soon after the birth of Dmitri, his father became blind, and the family were practically dependent upon the mother, Maria Dmitrievna Mendeleeva, who established a glass works near Tobolsk, on the profits of which she brought up and educated her large family. At the age of 15, Mendeleev was taken by his mother to St. Petersburg, and began the study of natural science at the physico-mathematical faculty of the Institute. After serving as a science master at Simferopol in the Crimea and at Odessa, in 1856 he became a privat docent in the university. Then, following a short period of study in France and Germany, he returned to St. Petersburg, and in 1866 he was made professor of general chemistry in the university. His reputation mainly rests upon his contributions to chemical philosophy and physical chemistry, notably on specific volumes, on critical temperatures, on the thermal expansion of liquids, on the nature of solutions, on the elasticity of gases and the origin and nature of petroleum. He died on January 31, 1907. End of chapter 6.